So in this lecture, we're going to talk about convergence problems and logistic regression. Convergence problems are also called non-existence of MLEs. So as you've calculated, we use maximum likelihood estimation to construct estimates for logistic regression parameters. Computing the MLE is an iterative process that's done numerically. As I've discussed, we can't do this by hand. And this typically results in obtaining parameter estimates that change very little as the steps of the procedure progress. And generally, when the change in the parameters or the log likelihood is deemed small enough, the procedure is said to have converged. However, in some cases, the algorithm fails to converge. And in this case, the estimates returned would not necessarily be accurate. And actually, this problem occurs much more often than you might think in practice. It's occurred for me several times, so it's important to know when it's happening and what you should do about it. Because when convergence does fail, we won't be able to rely on the MLE we won't be able to rely on the MLE parameter estimates from R or SAS if you're using SAS. And generally speaking, when convergence problems occur, they're usually due to empty cells in 2x2 tables. So for example, if all failures or successes have the same value of a binary covariate. And these result in very large estimated coefficients and standard errors. And this problem will affect the MLE estimation and walled tests all of the time, but sometimes the score and likelihood ratio tests will still be valid. So I'm going to go through a data example. In this data set, clinicians are interested in whether patients with osteosarcoma, a bone cancer, achieve a 3-year disease-free interval based on level of lymphocytic infiltration, or how many immune cells have entered the tumor area. And the following variables are available. We have disease-free, that's the outcome. 1 if the patient achieves a 3-year disease-free interval, and 0 if the patient does not. We also have lymphocytes, that's 0 if high, 1 if low, a binary variable. Gender, which is also a binary variable. And AOP, or osteoblastic pathology, which is also a binary variable. And then finally, we have a count variable, which just tells you how many people fell into each of these different covariate patterns possible. And here I'm entering that data set in R. So initially, the investigators are interested in a couple different models that just look at one covariate each. One with lymphocytes as the main covariate, one with gender, and one with AOP. And so we're going to run each of these models. And actually, the way I'm specifying the GLM statement here is different from what you've seen before. In this case, I just run the outcome against the covariate of interest, but I also use this argument weights equal count. And that's because of the way the data is set up, is where you have this count variable, which actually tells you the number of people that fall into each category. So you have to use the weights argument to make sure that you are accounting for all of these people in the correct manner. And then finally down here, I'm just creating a data frame that stores the coefficients for each of these different models so that we can take a look at them side by side. So then in the next slide here, I just print out that data frame, and you can see for the lymphocytes only model, we have beta 0 and beta 1, as well as for the gender and the AOP model. And for the gender and AOP models, the covariate values are reasonable, but you can see for the lymphocytes model, the covariate values are quite high. And so for each of these, so like beta 1, for example, e to the beta 1 is your odds ratio. and that's going to be e to the negative 17.9, which is really, really, really small. Basically zero. And similarly, the beta, the intercept value is going to be very, very large. So what happened? Again, you see, okay, the lymphocytes, and just for this model, if we print out the standard error, if we print out the summary, we can see that the estimates are quite large. The standard errors are huge. And the number of Fisher scoring iterations is 16, which is fine, but it's higher than we've normally seen for previous models, where it usually ends around 4. So it's taking longer for this model to converge. So there are a couple different numerical checking procedures we can go through to try to understand why this model is not behaving the way that we expect it to. So there are two, we can adjust aspects of the model fitting procedure to examine convergence. One thing we can do is increase the number of Fisher scoring iterations. The default is 25. The other thing we can do is decrease the tolerance. So the way that convergence is assessed is that you calculate values of the parameters, and then you figure out what the log likelihood is equal to at those parameter values. And with each iteration, if the log likelihood gets closer to stable, closer to some estimate, it doesn't change too much as you change the betas, then it's said to have converged. And the tolerance is just how close together those log likelihoods need to be for convergence to have been attained. And so if we decrease tolerance, then we have to have the log likelihoods closer together to have considered it converged. And the default in R for that is epsilon equals 1 times 10 to the negative 8th. And if we decrease that, it will take us longer to converge. So I'm going to fit 3 models here where I decrease the epsilon. I have different epsilon values to change the convergence criteria. In this case, and that's what this control argument is letting us do. We're choosing 1,000 maximum iterations of 1,000. You can go up to 1,000 iterations, though it's not going to necessarily go 1,000 times. It will stop when you reach the epsilon value chosen here. Here we're choosing epsilon of 1 times 10 to the negative 4. That's actually larger than the default. We're also choosing 1 times negative 10 and 1 times 10 to the negative 16th. And then I'm going to run those models. I'm going to store some results in a table, like the tolerance value that we defined, the log likelihood value that's calculated, the number of iterations it took for the log likelihood to stabilize based on that tolerance level, and then the values of the beta 0 and beta 1 coefficients for each of those models. So if we take a look at these results down here, we see for each of these models, we're actually getting the same log likelihood, which means the log likelihood is converging. It takes more iterations for the smaller tolerance values, which is what we'd expect to see. However, what's weird is that beta 0 and beta 1 are getting bigger and smaller. They're going to positive and negative infinity as you increase the tolerance. And that's because there's just not stability in this model for these estimates. So if you have a small tolerance, you have a more reasonable beta 0 and beta 1, but as you have lower tolerance, it's taking longer to converge, and the beta 0 is getting larger and the beta 1 is getting smaller. And because, and the reason that you still have the same log likelihood values for these different parameter estimates is that they're sort of canceling each other out. As beta 0 gets larger, beta 1 gets smaller, so they cancel each other out and still have the same log likelihood value. And if you were to decrease this tolerance even more, say like 1 times e to the negative 100 or something like that, you would see the same thing, where you have a log likelihood that's about negative 24.9. you'd have a whole bunch of iterations. And you'd have a beta 0 that's very large and a beta 1 that's very small. And so why is this actually happening? Well, it occurs because all of the failures, the values of the disease-free outcome equal to 0, have the same value of the binary covariate. They all have the value lymphocytes equal 1. And this corresponds to an empty cell in the 2x2 table of disease-free by lymphocytes. And this is called separation. So what do we actually do about separation? Well, wald tests are going to be invalid because the likelihood surface is too flat, leading to huge standard errors and instability in your calculation of beta 0 and beta 1. Likelihood and score test should still be okay, so you should still be able to calculate p-values based on that. You can also use Fisher's exact test, which is computationally intensive and can only be run in a model where there are no other covariates except for the one of interest, but it still is technically correct to use. You can also use something called exact logistic regression, which is computationally intensive as well, and the tools in R are really not that well developed for it. Or you can use this thing called Firth correction, which will give you estimates corrected by penalizing the log likelihood, and it's also easy to implement in R. So first I'm going to look at the likelihood ratio and score tests. So in this first model, I'm running an ANOVA statement that runs that lymphocyte model, compares it to the intercept only model. So it's just testing, both beta 0 and beta 1 at the same time. No, scratch that. I'm sorry. It's just testing the hypothesis of H naught that beta 1 is equal to 0. And in this case, using the likelihood ratio test, we get a p-value that's significant. Or we can use the score test. That's what this indicating RAW, which the score test is also called the RAW test. And this is also comparing to the intercept-only model. So this is also testing the null hypothesis that beta 1 equals 0. And we see the same conclusion from this test, that we reject the null hypothesis. Well, what about Fisher's exact test? We can run that as well. And we didn't get confidence intervals using the score or likelihood ratio test. We just got p-values. So the nice thing about Fisher's exact test is that it will give you a confidence interval. In this case, we still get a significant p-value for this model. However, our confidence interval includes 0. And in general, Fisher's exact test has less power than other tests and doesn't allow you to adjust for other covariates. Finally, we can use the Firth correction, which comes from the Logist F package and this Logist F function. And then you sort of call the model in the same way we did for using the GLM function. And it gives you some coefficients. So you can you can run it with other covariates, but you still get an actual coefficient value that isn't 0 for your lymphocytes. And so that can be nice to have and potentially use if you have this convergence issue. So what are the conclusions from this, and in practice, what would you do? Well, convergence issues like this are most likely to occur when you have small data sets. And if you run a logistic regression and you notice that for some covariates, the estimates are very large or very small and you have very wide confidence intervals or very large standard errors, it's important to dig deeper because your inference might not be valid. In particular, the walled type inference will not be valid, but sometimes you can use score likelihood ratio tests if you want to get a p-value for your particular parameter of interest. However, and then there are some alternative methods that to deal with this. Exact logistic regression in practice in R, that's just hard to do. Firth correction, which is much easier to implement. But what I actually do most of the time and would recommend is if that is not the covariate of interest, then just take it out of your model. And when you report the what you did in the paper, just make sure to mention that. Say you didn't include lymphocytes in your model because the cell sizes were too small and estimates weren't accurate.